We're given vector a and b and asked to find the cross product of vector a and b. We're going to find vector a crossed with vector b. When we find the cross product of two vectors, the result is another vector that is orthogonal or perpendicular to both vectors. So if we find the cross product of vector v and w, the result is another vector that's orthogonal to both vector v and vector w. And the direction of the orthogonal vector is determined by curling the fingers of your right hand in the direction of vector v to vector w. When doing this, your thumb points in the direction of the orthogonal vector. So looking at this picture here, if we find the cross product of vector a and b, and using your right hand, you point your fingers in the direction of vector a so that they would curl toward vector b when you close your hand, the cross product will be in the direction of your thumb. The easiest way to find the cross product is to evaluate this 3x3 determinant where the first row are the unit vectors I, j, and k, the second row are the components of vector v, and the third row are the components of vector w. We can also use this formula here, but it's probably much easier just to remember how to evaluate this 3x3 determinant than memorizing this formula here, even though the result is the same. So going back to our example, let's graphically show the cross product of vector a and b before we find this cross product. This purple vector here is vector a, and this red vector here is vector b. The cross product is this yellow vector here, which is orthogonal or perpendicular to both vector a and vector b. Notice how if you take your right hand and point your fingers in the direction of vector a so that they would curl toward vector b, your thumb would point upward in the direction of the cross product, which we see here in yellow. So as you rotate this, notice how the cross product is always perpendicular to both vector a and vector b. Now let's find our cross product. Again, we'll set this up as a 3x3 determinant, where the first row will be the unit vectors I, j, and k. The second row will be the components of vector a, so we have -2, 1, -1. The third row are the components of vector b, -4, 5, and 2. Now to evaluate this, we'll have a 2x2 determinant times a unit vector I minus a 2x2 determinant times the unit vector j plus a 2x2 determinant times vector k. So to find the elements of this first 2x2 determinant, we'll eliminate the row and column containing the unit vector I. So we'll eliminate row 1 and column 1. These four elements make up our 2x2 determinant. So we have 1, -1, 5, 2. And now for the next 2x2 determinant, we'll eliminate the row and column of vector j. So again, we eliminate row 1, but now we eliminate column 2. The remaining elements are -2, -1, -4, and 2. And then finally, for this third 2x2 determinant, we'll eliminate the row and column of vector k. So again, we eliminate row 1, but now we eliminate column 3. So the elements that remain are -2, 1, and -4, 5. And now we evaluate each of these 2x2 determinants. So for this first 2x2 determinant, we'll have 1 times 2 minus -1 times 5. So we have, again, -1 times 2, that's 2, minus -1 times 5, that's -5, times the unit vector I, minus, here we'll have -2 times 2, minus -1 times -4. Well, -2 times 2 is -4, minus -1 times -4 is +4, times the unit vector j, and then finally plus, here we'll have -2 times 5 minus 1 times -4. Well, -2 times 5 is -10, minus 1 times -4 is -4, times a unit vector k. Simplifying, here we have 2 plus 5, that's 7i. Here we'll have minus negative 8, that's plus 8j. And then finally here we have plus, this would be negative 10 plus 4, so that's plus negative 6k, or just minus 6k. Which of course, if we want, we can write in component form, where the x component is 7, the y component is 8, and the z component is negative 6. So this vector is orthogonal or perpendicular to both vector A and vector B, which we already saw graphed here in yellow. I hope you found this helpful.